Thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing today. Without further ado, I will pass it on to our presenters, and I will also go ahead and post the link to the 1324 room.
Hello, everyone. Um, Happy Friday. I wanted to just, before we get started, I was looking at the calendar for 1314, and I went ahead and made a slight change so that what we present today is for your assignments that are due this week. And so this is going to catch us up. That way, from now on, you'll be able to see that during that week assignments is what we're covering. And so what we're going to cover today is synthetic division and finding zeros. I will be sending whoever is on today a copy of the quadratic equation video from last semester. That way, if you want to see that, you can also view that as well. Okay. At any time, if you have any questions, please let us know. So what we want to do today is one of the big things in chapter 2 is finding this zero here. And so one of the ways to do it is graphically, just by looking at it. But we know that we don't often get a graph for our equations. So our goal is going to be to factor the equation. And so once you factor, it might look something like this. And each of these parentheses, we call them factors. So if you know that x equals 2 is a 0, then x minus 2 is going to be what we call a factor. So synthetic division is basically a shortcut for long division. And you can use synthetic division if you're dividing by a polynomial that is 1 degree x minus c. And in order to divide, one of the things that you have to do first is look at the coefficients in front of the variables, so the a, b, c, d here. And you want to list those here, and you always want to make sure that you arrange them in decreasing order by their degree. So in this case, the a is paired up with the x cubed, so that would go first. And then once we do that, if you're missing any, can everybody else see the slides? Give me a thumbs up if you can. Okay. So besides writing your coefficients, the next thing we need to do is to write down what k is. K is going to come from, or your divisor. In this case, if you look at x minus c, c is going to be your k that goes in here. Okay. So once you do that, then the first step is to bring down the a, and then we're going to multiply k times a, and whatever the product is, you're going to write on top of this line, and then we're going to go ahead and add those together. So b plus the product here, and then it's going to be a cycle. So then we would do the same thing, k times this number, we would put it up here, and then we would add it to the c, and it's just going to be a cycle until we're done. Okay, so it's going to be easier when we see it with numbers. Now the last number you get here, that's what we call a remainder. And whatever's before the remainder is what's going to make up our quotient. Okay, and we'll discuss these terms as we do the examples here. So if we have this example, x squared plus 5x plus 6 divided by x minus 1, we want to first identify what k is. So k is going to be 1. Okay, so I'm going to write the 1 on the left side, and then the next step is to list the coefficients. So in front of x squared, we have a 1. In front of x, we have a 5, and then we have our constant 6. And then our next step is to bring the 1 down, and then we're going to multiply 1 times 1 is 1, and then we're going to add, so 5 plus 1 is 6, and then we start the same process again. 1 times 6 is 6, and now we're going to add 6 plus 6 is 12, okay? And then the process ends here. So in this example, our remainder, which is the last number here, that's going to be 12. Our quotient, or our dividend, is x squared plus 5x plus 6. That's what we're dividing, that's what we want to divide into. And then we have our divisor, which is x minus 1 is our divisor. And then the last thing is going to be our quotient. Now the quotient, when you're ready to write it, notice that our dividend, the highest power was 2. So when you're going to write your quotient, this 1 will be the coefficient of a power less. So this 1 would be just 1 times x. And so I can just write it as x. And then we have the 6, so plus 6. And then you're going to write your remainder, so plus 12, divided by the divisor, x minus 1. So in this is the form that you want to write your answer. So we're going to do a few of these, and then we'll find the zeros that go, the zeros, which is the main point of why we even want to use synthetic division. Okay, so the first step here is to figure out what C is. So notice that in this example, we have x plus 7, but it would be best if this was written, we know that the k is going to be coming from something that looks with x minus c. So we can rewrite x plus 7 as x minus negative 7. Okay, if I rewrite it this way, now we can see that negative 7 is going to be our k. Okay, so now we want to put what goes in here. Okay, so what numbers will go in here? So those will be your coefficients. Make sure they're in descending order. So we have our 3. We have our 3. And then you have a 6, but notice that x squared comes first. So we want to put the 21. Then we have the minus 6 and the negative 42. Okay, so now we're ready to begin. So we bring the 3 down. It's negative 7 times 3 is negative 21. We're going to add 21 plus negative 21 is 0 times negative 7. That gives us 0 plus negative 6 gives us negative 6 times negative 7 is positive 42. And then that's going to give us a 0. Okay. So getting a 0 here is going to be something that we are going to be excited about, because then that means that our work is going to be done faster. Okay. So what is our quotient? So our quotient is going to be 3. We started with an x cubed, so we're going to go one less, so we get 3x squared. And then we have plus 0x and 6. We have a divisor of 0, a remainder of 0 divided by our divisor, which was x plus 7. And so instead of 0x, we can just get rid of it and write our answer as 3x squared minus 6. 0 divided by this is just 0, and that's why I didn't include it here. So let's try another example. So here we have x cubed, x squared, and 6. And then we are dividing by x minus 5. So this is already in the right form. So our k is going to be 5. Okay. And now notice that we're missing a term here. We went 3, 2, and then we should have had an x here, but we don't have one. So we want to make sure that we use a 0 to fill that missing term. So my coefficient for x cubed is 1. Then we have negative 3. I'm going to put a 0, and then we have a 6. So we bring down the 1. 5 times 1 is 5, plus a negative 3 is 2. And then we multiply again. 5 times 2 is 10, plus 0 is 10. 10 times 5 is 50, plus 6 is 56. So 56 is our remainder. And so our quotient, we will start with the 1. Our degree was a 3, so that means this should be x squared. So that's my x squared. And then I have a 2x and a 10, plus my remainder of 56 divided by x minus 5. And then that would be our answer. Any questions? So what is the purpose of synthetic division? And the whole purpose of that is that we're trying to find these zeros. And in order to find the zeros, when we get the remainder here of 0, then that's good news for us. Because from there, that tells you that this number k is going to be a 0. And so remember what I mean by a 0 is if you were to draw this on a graph, that means that at this point here, your graph is either going to touch it or cross it. And so by getting 0 here, that automatically tells you that this number is a 0. But the more important thing too is that your quotient, instead of having something like cubic, we're breaking it down to quadratic quotient. And once it's in quadratic form, then we have choices. We can either factor, use the square root property, or use the quadratic formula so that we can find the rest of the zeros. And so in this example, we can factor, and we'll do some examples. So right now I'm just illustrating why we use synthetic division. But if we factor this polynomial, then we get that x is a half and x is a half. And so in this example, we're going to have 3 zeros, -2, half, and half. Okay, and the half here is repeated, and that's also going to tell us something about the graph, which we'll talk about in a few minutes. So here, the rest of these slides are really going to be targeting section 2.5. And so again, the whole point of this chapter really is to find these zeros. And so this example here, I just wanted to show, notice the zeros here, x is equal to 2, x is equal to -1, and x is equal to 4. And notice what's happening with the graph. The graph is going right through the point, right? It's just going right through them. But if we look at this one, we have a -2 and a 2. So at 2, the graph crosses the point, but at -2, it touches and then it turns. So let's look at the zeros. We have a -2, which is this one. We have a +2, which is this one. And then we have another one, -2. Okay, and here it just touched. So the number of times that the 0 repeats is going to tell you whether the graph touches or whether it crosses. Okay, so on this side, we have -2, 0, and 2. So notice that x equals 0 appeared twice, and the graph just touched. So if the number appears an even number of times, like x equals 0 and x equals 0, then your graph is just going to touch and turn. And if it appears an odd number of times, then the graph is going to cross the point. And you want to know that information for when you have to graph the polynomial. Okay, so this fundamental theorem of algebra tells you that a graph is going to have an nth degree polynomial, should have n zeros. Okay, so what does that mean? In this case, the degree is 3. And so what that means is that altogether, you should have 3 zeros. Your zeros might be rational numbers, irrational numbers, or it can be a set of complex numbers. But all you know is that it should have 3 zeros. Here we have a 4 and a 6. So the highest degree is going to tell you how many zeros you're going to have. So in this case, we should have 6 total zeros. These are just some quick examples. If you want to find a 0, the first thing you want to do is change f of x so that it's equal to 0. And then you solve for x. So remember, the zeros are also called the x-intercepts. So if you add 2 on both sides, then we get x is equal to 2. Here, again, f of x, we change it to 0. This is quadratic, so one of my first things that I like to do is ask myself, does it factor? In this case, it does factor. And so I can set each factor equal to 0 and solve for x. So here I get x equals 3 and x equals 3. And then here we have 3 factors. So I can set each factor equal to 0. So x equals 0, x minus 2i equals 0, and x plus 2i equals to 0. And then I can solve for the zeros. These imaginary zeros, we cannot see them. For example, the graph might be up here somewhere, and so it's not going to cross the line. Okay, but they are zeros. So for example, here in this graph, well, we can just do an example. So this one is from the previous examples. Let me just go over it really quick. So it says find the zeros of the polynomial function given that x is equal to 4. So they tell me that 4 is a 0. That means that that's going to be my k. And then I write my coefficients here. I use 0 because it's missing the x squared term. And I did the work, and then I got a 0 here. Okay. If I didn't get a 0 here, that means that I did something wrong because they're telling me that x equals 4 is a 0. So my remainder better be a 0. So if I get the quotient, then I get x squared minus 4x plus 3. That comes from these three numbers here. And now notice that it's quadratic, so we can factor and find the other two zeros. Okay, so we have 3 zeros. So my big question here is, look at this example or look at the question, find the zeros of the polynomial function, given that x equals 4 is a 0, and then they give you this. So how is this problem different from this problem? What are we missing in this example here? Any ideas what we're missing? So in this example, they don't tell me that something is a 0. So we need to figure out what can we use to start the synthetic division. Okay, so to do that, we can use the possible rational zero test, theorem test. And basically what we're gonna do is divide the factors of the constant term divided by the factors of the leading coefficient. And that's gonna help us to find a list of possible rational zeros. And so what is a factor? Factors are just numbers that you can multiply together to give you that number. So the factors of 8 are 1 and 8, and 2 and 4. The factors of 24 are these numbers here. Okay, so the first step is to figure out what are the factors of the constant term. So the constant term is 9. So those factors are 1, 3, and 9. And what are the factors of the leading coefficient? In this case, 1. So the possible rational zeros, we divide them. And so I'm going to write them as plus or minus 1, plus or minus 3, plus or minus 9 divided by 1. So we just divide 1 divided by 1 is 1. 3 divided by 1 is 3. And 9 divided by 1 is 9. So here we have 6 numbers that we can use to try to find our zeros instead of using the infinite amount of numbers that we have. So let's start with 1. So if I bring down my synthetic division, 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Negative 9 times 2 is negative 7 times 1 is negative 7. If we add 9, we get a 2. So we didn't get a 0. So that means that this 1 is not a 0, and that does not help us. So I go to the next number. Now let me say one more thing before we move on. Let me go back to this slide. Notice here that I have the plus and minus because you want to include all the different factors. So we include the negative as well here. Okay, so that's where, so the next number that I like to try is going to be negative 1. So we do the same process. Negative 1 times 1 is negative 1 plus 1 is 0 times negative 1 is 0 plus negative 9 is negative 9 times negative 1 gives me a positive 9. Okay, so let me see what happened here. I think there's a mistake. Oh yeah, so thank you, Ruben. So this should be a negative, right? So I copied it wrong. Notice that this is a negative 9. So negative 9 plus 9 is 0. And so yes, that's gonna make us happy because we know that negative 1 is a 0. So now, since this has degree 3, we're missing 2 zeros. How are we gonna find them? We're gonna use the quotient. So my quotient is gonna be x squared minus 9. So I can set my quotient equal to 0. So I'm gonna add 9 on both sides, take the square root, and so the square root of 9 is plus or minus 3. So my zeros are gonna be the negative 1 that I got from the synthetic division, and then the plus 3 and the negative 3. Okay. So something that we want to do for problems that are going to be, they're going to ask us to do the factors. If you have a 0, to get the factor, you put everything on the same side. So this -1, I'm going to bring to the left side by adding it on both sides. So I end up with x plus 1 as my factor, and this will be x plus 3 and x minus 3. Right now, the question is only asking for the zeros, but the factors will be needed for a different problem. Okay, so that was, let me go a little bit slower on this one since the other one was kind of introducing. So here it says find the rational zeros. So first step is you want to have a starting place. So I recommend the rational zero test. Your constant term is 1, so the factors of 1 are plus and minus 1. And then you want to find the factors of the leading coefficient. In this case, your leading coefficient is 2. So my factors are 1 and 2. So I'm going to put those in the denominator, 1 and 2. And then we're going to divide. So 1 divided by 1 is 1. And then we have 1 divided by 2 is a half. So we have these 4 possible rational zeros. So we can pick one. I always like to pick one first because it just seems easier to pick. So I'm going to bring down the 2. 1 times 2 is 2, plus 3 is 5. 5 times 1 is 5, plus 0 is 5. 5 times 1 is 5. And so we get 4, so this is not a 0. So x equals 1 does not help me here. So I go on to the next one, which I can use -1. And we're going to bring down the 2. Times -1 is -2, plus 3 is 1. 1 times -1 is -1, plus 0 is -1, times -1 is a +1, and we get 0. So yes, happy face, we get a 0 here. That means that this is a 0, and now I need to find the rest. So to find the rest, we need to find our quotient. Since I have a degree 3, this 2 is going to start with degree 2. So my quotient is going to be 2x squared plus x minus 1. And the good thing is it's quadratic, so we have choices. We can either use the quadratic formula or we can try to factor. If you try to factor, I always give myself a minute. If I can't get the factors, then I move on to the quadratic formula. And the reason is maybe it's not factorable. Okay, in this case, it does factor. 2x minus 1 times x1 equals 0. Set the two factors equal to 0 and solve for x. So here we add the 1 and then divide by 2. So x is a half, and then here I'm going to subtract by 1 on both sides, so x is -1. So I should have 3 zeros, and so my 3 zeros are -1, a half, and then my third zero comes from the one I use for synthetic division. So these are my zeros. And if you were to write okay, well, let me mention this here. Notice that x equals -1 and x equals -1 appears twice. So we say it has multiplicity of 2. And so what that means is when you're graphing, let me just draw a quick graph here. At -1, you have a 0. So your graph is either going to go touch here and come up, or maybe it's coming from down here. It's going to touch and then go down. So it's going to be one or the other. The important thing is that it's going to be touching, and then it's going to turn back. So it's going to touch and turn. Okay.
Very good, Yvette. So let's continue with finding the zeros. So let's read the problem. Find the rational zeros of the polynomial function. Okay. So we're going to use the rational zero test to find all the zeros because we don't want to try any infinite numbers. We want to limit our possibilities. Okay. So again, our constant is 4. So our our terms for 4 are 1, 2, and 4. Our leading coefficient is 1, so it's just the 1. Now, I also want to mention that when we're doing this list, okay, we don't want to include duplicates. So we always have the plus and minus 1, plus or minus 2, and plus or minus 4, even though these numbers might appear more than once. Also, WebAssign sometimes doesn't recognize this symbol, so it's when they ask you to write the list, you can write them just like this. This is what they mean when they write a list, is just writing them all individually, okay? Again, in case you don't have the plus or minus symbol. All right. So if we use synthetic division, okay, we start off with 1, and that's always your best one to always start with. You never know, that 1 could be one of your zeros. So when we do the 1, when we're using synthetic division, again, we bring down the 1. 1 times 1 is 1. Minus 4 plus 1 is a minus 3. 1 times minus 3 is a negative 3. So 0 minus 3 is negative 3. 1 times a negative 3 is a negative 3. And 4 negative 3 is equal to 1. So since in our remainder we didn't get a 0, then 1 is not a factor. So we try negative 1. Let's try negative 1 again. And if we go down the list, we see that 4 minus 5 gives us a negative 1. So again, our remainder is not 0. So negative 1 is not one of our factors either, or our zeros. So here we try 2. Okay. Again, 2 gave us a remainder of negative 4. So hence 2 is not a factor. We try negative 2. We get a remainder of negative 20. So this one is also not one of our zeros. Okay. We try 4. Okay. We see that when we use 4, we get a remainder of 4. So 4 is not one of our zeros. We try negative 4. We get this very huge number, is 132. So none of these are our zeros. So, and we tried all of our lists. So if we were using, we had this problem on the computer, because it asked us to find the rational zeros, okay, we would write does not exist. But this doesn't mean that this polynomial doesn't have zeros, okay? So if they were just asking for any zeros, we would have to think about or include our complex zeros. So we could see this in this graph, okay? So if we would graph this, we see that these zeros are complex, okay? But again, for our computer, in this particular problem, we would just write does not exist, okay? All right, so let's go ahead and do one more example, okay? So what I want to do is I want to give you a couple of seconds for you to list the possible zeros for this, okay? You're going to use the rational zero test to list the possible zeros. Okay, so the first thing we notice is that our constant is 24, so we'll have the multiples of 24. Our leading coefficient is a 9, so we'll get the multiples of 9, okay? So again, so for our constant, the multiples of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. For our leading coefficient 9 are 1, 3, and 9, okay? So when we divide these numbers, we have this very huge list, right? We have plus or minus 1. So as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, right? Possible zeros, but these are possibles. And as Ms. Chuka stated, this polynomial should have at most 4 zeros. Yes, so again, these are just possible. This doesn't mean that these zeros are it. And again, hopefully we do find one, and just like the previous example, maybe none of these are the zeros, but hopefully we do find one of the zeros in here. All right, so again, always start with 1. Start with 1. When I use 1, using synthetic division, I see that my remainder is 30, so 1 is not a 0, okay? Let's try negative 2, okay, just to speed up the process. Again, so I'll take it slow to review. When we're using synthetic division, the first value will bring it down. Negative 2 times 9 is a negative 18. And I'm going to add negative 9 with negative 18, gives me a negative 27. And do the process again. Negative 2 times a negative 27 is going to give me a positive 54. So negative 58 plus 54 is a negative 4. Then I'm going to multiply -2 times a -4. That's going to give me a +8. So 4 plus 8 is 12. And the -2 times a +12 gives me a -24. And when I add 24 with a -24, I get a 0. So happy, right? Happy news. So since our remainder is 0, this is telling us that at x equals -2 is a 0. Now, we're going to get our quotient, okay? Our quotient is this that we have here. So we write it out. Again, we had a 9, and it's 1 degree less than the 4, so it's going to be 9x cubed minus 27x squared minus 4x plus 12. But we can't factor, or we could. It could be a little complicated. We can't use a quadratic equation because this is not a quadratic polynomial. So what we can do is we can apply synthetic division again to simplify even further. Okay, so let's repeat the process. Let's take the 9x cubed minus 27x squared minus 4x plus 12, and let's simplify it one more time using synthetic division. So again, these were our list of possible zeros. So again, just to speed up the process, I'm going to use 3. Okay, so again, we bring down the 9. 9 times 3 is 27. -27 plus 27 is 0. 3 times 0 is 0. -4 plus 0 is a -4. And 3 times a -4 is a -12. And 12 minus 12 is 0. So yay again, right? So we got a remainder of 0. So that means that x equals 3 is a 0 for this polynomial. Okay, so again, we're going to get our quotient that we have. And again, we didn't write it out, but again, we started with a cube, so we have a 9x squared. We didn't write it out, but it's 0x. Again, it's just 0. And we have our constant, -4. Okay, so again, you can approach this several ways. The way that I always like to do is factor these. Okay, I can see that this is a difference of squares, but let's practice our square root property. So let's find the 0 using our square root property. So the first thing that I'm going to do is I'm going to add 4 on both sides. It's going to give me 9x squared is equal to 4. Divide by 9 on both sides. So we have x squared is equal to 4 over 9. And then to get rid of the square, I'm going to take, again, the square root of both sides. So the square root, we like to say that it cancels the square, leaving us with x. And we want to simplify the square root of 4 over 9. So this is going to give us plus or minus 2 over 3. Okay, so when we put it all together, okay, we had a 0 at x equals -2 from our synthetic division. We had a x equals 3. Again, we use synthetic division to find another 0. And then we use our square root property to find the remaining 2 zeros. So the zeros here are, again, x equals -2, x equals 3, x equals 2/3, x equals -2/3. So again, if I wanted to find the factors, all I have to do is just move the numbers to the other side. Yes, so when I write my factors, again, add 2 on both sides, so I have x plus 2. Subtract 3 on both sides, I have x minus 3. Subtract 2/3 on both sides, I have x minus 2/3. Add 2/3 on both sides, I have x plus 2/3. Now, another thing that I also want to mention to you is these are all linear factors, and they're linear factors because I only have a 1 here, okay? So be very careful also in your homework. You may happen to get square factors, and on your computer questions, they ask you to list the linear factors. So please make sure you're aware that the type of factors that you're answering, okay? All right, so let's consider this problem again, the problem that we had done already, okay? So listing all the zeros, okay? We use synthetic division to simplify to make it into a square polynomial. We used our square root property to find the remaining x's. So again, the zeros for this particular problem, our x equals -1, x equals -3, x equals 3. Our factors are x plus 1, x plus 3, x minus 3. Okay. Any questions? All right. So if we wanted to now sketch the graph, we have all the tools to go ahead and do that. Okay. So we have our zeros, and we want to make a list when we're graphing. We want to make a list of checklist to get an accurate graph um, when when solving for these. So we always want to look at the end behavior of the graph. We want to look at the multiplicity. Again, as Ms. Chuka explained, if we have repeating numbers, that means that that zero is just touching, it's not crossing the graph. Okay. We want to have the zeros, which we've done, and also we want to find the y-intercept. So, and that one's hopefully easy to see. If I wanted to find the y-intercept of this, what I want to do is I want to replace x by 0, okay? And that's going to give me the y-intercept. All right. So again, to review the end behavior of the graph, if we have an even function, okay, and our leading coefficient is a positive, our graph is going to be pointing up, right? Or you can, as the book states, it rises on the right and rises on the left, okay? If our leading coefficient is a even function, and an and our leading coefficient is a negative number, excuse me, our graph is going to be pointing down, or it falls to the right and falls to the left. If our polynomial is a odd function, okay, and our leading coefficient is positive, okay, it's going to rise from the right and fall from the left. Or I like to say, it's if it's positive, it's always increasing, it's always going up, right? So if we have an odd function and our leading coefficient is a negative, okay, it's going to rise from the left and fall from the right, or like the way I like to think of it, it's always going down. Yes? All right, so this is our end behavior. So what will our end behavior be for this polynomial? So we can see that this polynomial is an odd function, so it's going to be either of these two. Then our leading coefficient, we know it's positive. So then the graph that we're going to be looking at is this one right here. Okay. All right. So again, to review multiplicity, if we had a repeating zero, that means that the graph is going to touch. So as an example for this function x squared, we see that here the vertex of this parabola is here at 0, 0, right? So this means that it gave us two zeros. So we had when we solve for the intercept using r square root property, x is equal to 0, and we can also see it as a product property, right, or a zero property, that in order to get a 0 from two multiples, either one of them is 0 or both of them are 0. So we have a double 0. So again, our multiplicity for this problem is 2. Okay. All right. So again, reviewing an odd function, okay, using our square root property, or our cube root property, excuse me, we have x is equal to 0, so it gives us one of our zeros. And to use our zero property, okay, we have the three zeros here, the 0, 0, 0. So this repeats 3 times, okay? So we have a multiplicity of 3, okay? All right. So let's go back to our example. So we have our end behavior, which we know it rises on the right and falls on the left. We know that it doesn't have any duplicate zeros, so all these zeros cross our graph. They're not touching our 0. We found that their y-intercept was equal to -9 by setting all the x values equal to 0. Okay, and this is as an ordered paired answer. Okay, so when we're graphing, we can plot, and I don't think we have the plot, so let's go ahead and plot. All right, so here we had as let me go back. Didn't write it. So we have a zeros at -3, -1, and 3. So let's do this. We have at -1. I need to write it. 3 and -3, excuse me. All right, here we go. We have a -3, we have at 1, and we have at 3, okay? And I know because my end behavior, again, I know that it rises from the right and it falls on the left, and because I know that these values cross at these points, okay, I know that my graph, okay, change the color here so it makes it stand out. Now, I did a rough sketch just because I know that on your computer online homework, and you have a multiple choice on your graph. So this will give you a very, very good sketch as far as choosing the right graph. But if I wanted to be specific, I would want to do a list of numbers. Okay, I want to do a table just to get a more accurate graph. I also know that my graph, oh, I forgot one of my zeros, right? I know that my graph crossed at 9, I believe, right? So my y-intercept was 9. So something over here. But if I wanted to be specific, again, I would choose just random values for x and plug it into my function, okay, to get a better accurate. But again, this is a good way to get a sketch on the graph, okay? All right. So, so here we have some examples on choosing values for x, and chose here -2. So when I plugged in -2, I got a +5. Here I chose a 1. So when I plugged in 1 to my function, I got a -16. When I plugged in 2 again, I got a -15. So again, here's a computer generated much better picture than what I have. And actually my graph, I had, again, I wrote it down wrong. I was using a +1 as a 0, but the answer is a -1. So I have a -1 right here, okay? And again, my y-intercept was -9. So we don't see it on the graph, but our graph is crossing the y-axis at -9, okay? So again, this was just a good idea, just so you could see that we can come up with a good sketch of a graph by finding the zeros, knowing the end behavior of the graph. Okay. All right. Let's try this example though. Find a polynomial function with a real coefficient that has the given zeros. So now we want to work backwards. What they're giving us now are the zeros, and we want to find the polynomial. So to do this, what I'm going to use is the linear factorization theorem to find this polynomial. And the linear factorization theorem says that if I have all the factors, 0 factors of a polynomial, and I multiply them all together, that's going to give me back the polynomial. Okay. So the first thing that I need to see is that these are my zeros, so I can set them up as x equals 3 and x equals -4i. And again, we know that I is an imaginary number, and our goal is to have this polynomial with a coefficient, a leading coefficient, the degree of the polynomial, and all these factors being added up to where we get a constant. Yes, as an example, this is an example. X cubed plus 2x squared minus 2x plus 4. Okay, so let's go ahead and do this one. Let's go ahead and solve the zeros. Okay, so I know that my goal here is to have a degree 3 polynomial, and I saw that from here because, again, I have an imaginary number and it has a -4, and I know that when I have an imaginary number, I have a square root, right, that is being taken, and not only it's a square root, but it have a negative square root number. So I know that when I take the square root, I always have the negative and positive. So that's why I rewrote the x plus 4i, because again, I have these two possibilities, and I see that this gives me my 3 zeros, or the list of factors, right? All right, so again, I have the zeros. I have x equals 3, x equals negative 4i, x equals to 4i. I'm going to write down the factors. So the factors are x minus 3, x plus 4i, and x minus 4i. So again, I'm going to use the linear factorization theorem to get my polynomial. And again, the linear factorization theorem says that if I multiply all these factors together with a constant, I would get my polynomial. Now, in this particular problem, they're not asking me for a particular polynomial. They just want me to write the polynomial with these zeros. So I'm going to leave the constant just as an an for right now. Okay, so I'm going to just do FOIL. Okay. So the first two that I'm going to multiply is x plus 4i and x minus 4i. So when I multiply x times x, this gives me x squared. X times a minus 4i is a minus 4ix. And then now the 4i times x is a positive 4ix. And a positive 4i times a negative 4i is a negative 16i squared. Okay. All right. Combine my like terms. The minus 4ix plus 4ix cancels out, becomes 0, leaving me with just the x squared minus 16i squared. I know that I squared is a negative 1. Okay, so I'm going to replace that with a negative 1. So negative 16 times a negative 1 is a positive 16. So then I have this polynomial, a sub n times x minus 3 times x squared plus 16. I'm going to go ahead and do FOIL again. I'm going to multiply this term by these two terms and negative 3 by these two terms. So when I do that, okay, I get x cubed plus 16x minus 3x squared minus 48. Do I have terms to combine? I don't, but I don't like it like this. I like to put it in standard form where it's in decreasing order, okay? So I'm just going to rewrite it as x cubed minus 3x squared plus 16x minus 48. And again, on this particular problem, they didn't want me to be specific, a specific polynomial. So since it's a general polynomial, I'm going to substitute a sub n by 1. Okay, so if I plug in 1 for a sub n, just as an example, I would multiply, if I had a number here, I'm going to multiply this number to all of the terms in my parentheses. So 1 times x cubed is just going to give me the x cubed. 1 times a minus 3x squared is just a minus 3x squared. 1 times 16x is just 16x. And 1 times a minus 48 is a negative 48. So when they give you the zeros and they want you to find the polynomial, you're using the linear factorization theorem to do this. So let's do another example. Okay. Now, this particular example is right off your homework, but on this particular one, they do want a specific polynomial, and I know that because they're giving me this extra piece of information that didn't give me before. They're telling me that the solution point, when I plug in 0 to my function, the answer's got to be -8. Okay, so this is going to play a key role to getting the specific polynomial that they want. So let's look at this. They want me to find a polynomial of degree 4, and they're giving me these zeros. Now, here I only see 3 zeros, but again, they're giving me I. Again, I is an imaginary number that comes from a square root, so I know that I have 2 values here. So let's go ahead and start with that. Let's write down our zeros. Our zeros are -4, +1, and then I and -I. Okay, so my factors are x plus 4, x minus 1, x minus I, and x plus 5. Excuse me. So I'm going to multiply all these factors together. Okay, so let's just go in order. So we'd start with this pair, which is going to give me x squared minus ix minus, excuse me, x squared plus ix minus I squared. Again, I know my I squared is a -1. Oh, I combine my like terms. I know my I squared is a -1, so replace that. It's going to give me x plus 4 times x minus 1 times x squared plus 1. Now I'm going to do these two terms. Okay, these two terms are going to give me x cubed plus x minus x squared minus 1. Again, I don't have any like terms, but I'm going to rewrite it just because, well, I didn't show my work here, but I would rewrite it first and then multiply the x plus 4 to this polynomial, which gives me this big list. So let's go ahead. Can we combine terms? So, and I just go down the list. So I have an x with a exponent 4. Do I have anything with an exponent 4? I don't. I have an x squared here. Oh, and I have another x squared here. So I know that this term and this term combine with each other. So a positive x squared with a negative 4x squared is going to give me a negative 3x squared. Okay. Let's choose another color. Okay, I know that I have a negative x cubed and I have a positive 4x cubed. So I can combine those two terms. So these are like terms. It's going to give me a positive 3x cubed. And then I have a constant. I have a degree 1, right? So I have a negative x and a positive 4x. So a negative x plus a 4x is a minus positive 3x, and I have a lonely constant. That one doesn't combine with anything, just like the x4. So my polynomial is this. Okay, so again, we have this a sub n term, which is our constant term. How are we going to get that value? So now this is where this comes into play. So this says that when I plug in 0 to my function, this is going to give me, it should give me an answer of -8. So that's what I'm going to do. What this is telling me is that when this polynomial, when I plug in 0 to all my x values, the answer has to be -8. Okay, so when we do this, 0 to the 4 is 0, 0 cubed is 0, 0 times 3 is 0, 0 squared is 0, 0 times -3 is 0, 3 times 0, that's 0, so 0 plus a -4 is just a -4. Okay, so to solve for a sub n, I'm going to divide both sides by a -4, and this is going to give me a sub n is equal to 2. So to get my answer, I'm going to replace a sub n with 2. Okay, so let's go ahead and do that. So we have 2 times our big polynomial, x to the 4th plus 3x cubed minus 3x squared plus 4x cubed plus 3x minus 4. And I'm going to distribute the 2. I got to multiply. It's very important that I multiply this 2 to all of my terms in my polynomial. So when I do that, 2 times x to the 4th is 2x to the 4th. 2 times 3x cubed is 6x cubed. 2 times a negative 3x squared is a negative 6x squared. 2 times 3x is a 6x. And 2 times a -4 is a -8. Okay, so I found my polynomial using my linear factorization theorem and the solution point to get the polynomial requested. Okay. Now, again, as Mastuka said, this section is very important, is finding zeros. And one of the major tools that you just witnessed is using synthetic division to help you simplify the polynomials to find the zeros. You're also, whenever they don't give you the zeros, you have the rational zero test to find possible zeros. That way you're not choosing numbers at random. You have a more centered list to choose from to find your possible zeros. Okay, so I know I have a few minutes. We finished a little early. Does anybody have any questions? Ms. Chuka, anything that you would like to add?
No, I was just gonna say, for next week, we'll cover, what is today? We'll be week 5. We'll cover a review for exam 2. That was it.
So
Thank you for coming today.
thank you all for joining us. Again, this session is recorded, so thank you so much. Now you're welcome to stay. We have wonderful tutors. If you want to go over some problems that we went over, or you have some problems that you have questions on, please stay and visit our tutors. Thank you.